Have you ever stopped to think about what happens when you click on an icon? I mean, it just feels instant, right? But underneath that incredibly smooth surface, there's this frantic high-speed ballet of parts all working together against some pretty incredible odds. So today, let's pull back the curtain and see how your computer really thinks.
So here's the central mystery we're diving into. Your computer's brain, the CPU, is just unimaginably fast. But the places it has to get its information from, your storage drives, are by comparison just painfully slow. This massive mismatch should, by all rights, bring your entire computer to a grinding halt. So, how does anything ever get done?
And this really shows you the scale of the problem. We call it the Great Speed Mismatch. Okay, so the CPU thinks in nanoseconds. A fast SSD, that takes microseconds to find data. That's 1,000 times slower. An old-school hard drive, we're talking milliseconds. That's 1,000,000 times slower. It's kind of like a genius professor who knows the answer instantly but has to wait for a book to be shipped from another continent just to confirm it. It's a huge bottleneck.
Okay, so to solve this, engineers came up with a really clever middle ground, and the first layer of that solution is something you've definitely heard of, random access memory, or just RAM. The best way to think about it is as the CPU's temporary workspace.
Now, RAM is what we call volatile memory. And that workbench analogy, it's perfect. As long as the power is on, you can lay out all the tools and plans you need right there. But the second you turn the power off, poof, it's gone. The bench is wiped completely clean. It doesn't hold on to anything permanently. And you can contrast that directly with non-volatile memory. This is your permanent library, your SSD or your hard drive. This stuff holds on to information whether the power is on or off. So you've got this really fundamental split, a super fast but temporary workspace, and a much slower but permanent archive.
And here's how they work together, which is pretty cool. When you go to launch an app, your computer copies all the necessary files from that slow, permanent library, the SSD, and spreads them all out on that fast, temporary workbench, the RAM. Now the CPU has everything it needs for the job right there in front of it, ready for instant access.
But here's the twist. Just when you think RAM has solved the whole problem, you find out something kind of mind-blowing. From the CPU's point of view, even RAM is slow. The speed gap is still so enormous that this high-speed solution actually feels sluggish to the processor, which means we need another layer, an even faster one.
And this brings us to the CPU's true inner circle, the cache. This is a tiny, incredibly fast, and very, very expensive type of memory that's built right next to, or sometimes even inside the CPU core itself. This is the ultimate solution for feeding that hungry processor the data it needs, instantly.
This analogy, which came from a Reddit discussion, is just perfect for understanding this whole thing. Seriously. If your SSD is on the moon and your RAM is the entire city you live in, then the cache is your immediate workspace. L3 cache is like your whole office building. L2 is the drawers right there in your desk, and L1, well, that's the piece of paper sitting right in front of your face. The difference in speed is literally that extreme.
So breaking it down, you have these different levels. Level 1, or L1, is the tiniest and the fastest. It holds only the most critical immediate instructions. Then you've got L2, which is a bit bigger and acts as a backup. And finally, there's L3, the biggest of the caches. It's shared by all the processor cores, and it acts as this large, high-speed pool of data the CPU checks before it has to make that long, slow trip out to the city of RAM. Okay, so we've got this incredible hierarchy of memory, right? From the moon all the way down to the paper on your desk. But how does the CPU actually use all of this? Well, that's where the computer's most fundamental process comes in. It's called the fetch-execute cycle.
It's a really simple but totally relentless loop. First, the CPU fetches an instruction from memory. Next, it decodes that instruction to figure out what it's supposed to do. Like add these two numbers. And finally, it executes the command. Then it just starts all over again. Fetch, decode, execute. And that cycle repeats millions, actually billions of times every single second. Each one of those fetch steps is a request for data. And this is why that memory hierarchy is so incredibly critical. The cache system is constantly trying to predict what the CPU will need next and have it sitting right there in L1 so that the fetch step is instantaneous. Any delay at this stage is what makes a computer feel slow.
So, you might be wondering, if L1 cache is the fastest, why don't we just build a whole computer out of it?
Well, that brings us to the fundamental trade-off that governs pretty much all computer design, the relationship between speed, size, and of course, cost.
And, even down at the slowest end of the hierarchy, what we were calling the moon, speed makes a huge difference. A standard SATA SSD is already pretty quick, but a newer NVMe drive, it connects more directly to the CPU, kind of like a dedicated superhighway, and it can be over 10 times faster. Just upgrading that one part can have a massive, noticeable impact on how fast your computer feels.
So here's the crucial point, the main takeaway. The entire memory system is a big balancing act. The rule is simple. The faster the memory is, the smaller its capacity, and the more expensive it is to make. It's an unbreakable law of computing. That's why we have tiny, expensive caches, larger and cheaper RAM, and then these huge, really affordable storage drives. It's a tiered system born out of pure physical and economic necessity.
And that is the aha moment. This is exactly why adding more RAM or swapping out an old clunky hard drive for a modern SSD can feel like you just got a brand new computer. You're not actually making the CPU any faster. You're just reducing the amount of time it spends sitting around waiting for data. You're unblocking that data pipeline and letting that brilliant professor finally work at full speed.
Which brings us to a final, really fascinating question. This whole elegant hierarchy was designed to solve this one big problem, the speed mismatch. But as CPUs continue to get exponentially faster, the pressure on this system just keeps growing and growing. So what comes next? What new, even faster layer of memory are we going to have to invent just to keep feeding the insatiable brain of the computer?